Hello, my name is Trent Belak, and we are the AP Physics class of 2021 presenting the concept Rotational Dynamics completed through both online and in-person labs as a class. The objective of this lab was determine the relationship between angular acceleration and torque, using Newton's second law and applicable formulas. The completion of this lab was made successful by using the pulley, finding angular acceleration and torque, and interpreting the graphs to calculate rotational inertia.
To begin, the virtual component of this lab consisted of 3 online simulations. First, there was an imitation of different objects rolling or sliding down an inclined plane. Here, it was distinguished that the mass distribution and friction dictated the order the various objects reached the bottom. Also, the angle of inclination did not affect the order of the objects. The second part of the virtual lab demonstrated how the rotational inertia of an object affects the percentage of the energy utilized for translational motion versus rotational motion. The smaller coefficient of inertia equation for each object, the higher the translational kinetic energy in comparison to the rotational. The third and final portion of the virtual lab showed how net torque and rotational inertia affected the angular acceleration of a rotating object and experimentally determined the mathematical relationship between net torque, rotational inertia, and angular acceleration of a rotating object. Angular acceleration and net torque have a direct relationship, and linear acceleration is related to angular through the radius.
This is our rotational motion sensor that calculates the rotations as the paper clips go down. That's connected to the lab quest that goes through LoggerPro through the computer, which calculates the stuff on the graph that we got familiarized with last year in honors physics.
As you can see demonstrated through the graphs, we measure the angle versus time and the velocity versus time.
So we're going to use the computer to take the data. When I click collect here, it's going to appear on the graphs. Whenever she releases that wheel at the top on the rotational motion sensor, the mass of the paper clips is going to cause the entire thing to move and spin, and it's going to measure the data for it as such.
The in-person lab required inertia to be known first, so a variety of masses were hung from the string attached to the step pulley. Then the string was wound around the second step of the step pulley before being released and allowing the tension from the gravitational force on the masses to unwind the string and rotate the step pulley. The slope of the angular velocity versus time graph, which represents the angular acceleration, also known as alpha, was then recorded. After using the equations a equals r alpha, t equals m times g minus a, and t equals r big T, with the constant variable r equals 0.0145 meters, t was found for each trial, then plotted on a graph of t versus alpha to find I. The slope of that graph yielded an I value of 4.59 e to the negative 6 kilograms per meter squared. Once the experiment began, it was time to fill in our procedure. We had a data table starting with mass. The mass was the paper clips pulling down the string influencing the system. The computer aided us to get our alpha, and now we had our R-step calculated in the pre-lab and our mass in our alpha. With that, we had more than enough to begin our equations, calculating the A, the T, and the torque.
When determining the inertia of the rod, the same steps were followed with the addition of finding the rotational inertia of the rod. The slope equals 5.45 times 10 to the negative 4th kilograms meters squared. The rotational inertia of the rod, or the 1/2 m rod L rod squared, equals 5.46 times 10 to the negative 4th kilograms meters squared. Lex pyramidal equals 5.4 times 10 to the negative 4th kilograms meters squared, and percent error equals 0.183%. Finally, when determining the inertia of the rod with the masses, and the same steps were once again followed with the addition of finding the rotational inertia of the rod and the masses. The slope equals 4.53 e to the negative 3rd kilograms meters squared. The rotational inertia of the two black masses, or 2m mass r mass squared, equals 4.2 e to the negative 3rd kilograms meters squared. The rotational inertia of the rod, or 1/2 m rod L rod squared, equals 5.46 e to the negative 4th kilograms meter squared. Theoretical equals 4.78 e to the negative 3rd kilograms meter squared. Experimental equals 4.52 e to the negative 3rd kilograms meter squared. And percent error equals 0.1105%. This is all proof that success was found by investigating the relationship between torque and angular acceleration. Angular acceleration data for objects subjected to the torque was collected, and the slope of the linearized graph was related to the system parameters. Put more clearly, the angular acceleration is related to torque through the multiplication of inertia.